Hello, my name is Salem. I will be doing a K-map review, in particular for the class ECE 2610, Digital Logic Design. Now, you may have taken K-maps, but we're going to have this video be a bit of a review as these can be a little bit challenging and can require quite a bit of practice. So before we get into any of these practice problems, let's just go over the basics. So you have two forms. You have sum of product, right? And you have product of sum. So sum of product is where you circle the ones in a K-map, and product of sum is where you circle the zeros. And so a sum of product, the final equation you get is going to be statements that are ANDed, and each of those ANDed statements are going to be ORed together. So my example right here is AB plus BC. That would be a sum of product. Now for a product of sum, it'd be in reverse. You'll have ORed statements that are ANDed. The example here is A or B and C or D. Now, with K-maps, or a Carnegie map, each cell must differ by 1 point, by 1 bit rather. So inside our 2-variable Carnegie map, you have the numbers going from 0, 1, 2, 3. Now, if you have a 3-variable one, you can see it looks a bit different. If you look at the BC bits, it goes 0, 0, 0, 1, 1, 1. Now, it goes to 1, 1 because that is a difference of 1 bit. If it were to go from 0, 1 to 1, 0, that'd be a 2-bit difference because 0, 1 has 2 different bits compared to 1, 0. The 0 switches to a 1 and the 1 switches to a 0. And that is not possible when doing K-maps. It will not work properly. Now, at least in ECE 2610, you won't have to worry about any Carnegie maps that are past 4 variables. Now, you can write these out like this, and as long as you memorize the process, or at least remember that things must differ by 1 bit, it'll make your life a lot easier. Additionally, that points out a few tricks. For example, you can circle at the edges. So you can circle the bits that are under 1, 0 over here, as well as these bits over here. The reason why? Because those bits differ by 1. 0, 0 differs from 1, 0 by precisely 1 bit. It is compatible. Now, as long as you remember that, you'll be good. Another big rule, you can only circle in amounts that are base 2. What that means is you can circle 1 thing, 2 things, 4 things, so on and so forth. You cannot circle 3, 5, or any form like that. As long as you circle under base 2, you will do great. So let's get started. Now, our first example here, we have a 2-variable equation here. You have 0, 0, 1, 1, 0, 1, 0, 1, and our F statement being 1, 1, 0, 0. So let's just go ahead and plot this. You have our A bit, you have our B bit. Now, since this is 2 variables, we can only have 2 possibilities. B can be 0 or 1. A can be 0 or 1. Let's draw this out. And there we go. Now recall, this is 0, this is 1, this is 2, this is 3. You don't believe me? Write it out. AB, 0, 0, 0, 1, 1, 0, 1, 1. This is binary 1, binary 2, and binary 3. Now, let's actually use this K-map to get our simplest form. So at 0, 0, we have 1. At 0, 1, we have 1. At 1, 0, we have 0. And at 1, 1, we have 0. Now, with a K-map, you want to circle as much as you possibly can, as that will minimize your equation. How do we minimize? You need to look at what changes when you circle. What I mean is, in this case, if we are to write this in sum of products form, so if we were to describe this with our ands and ors, we will then go ahead and circle our ones. To draw the biggest circle possible, we will draw a circle around those two bits. Now, if you look at this, you have A is equaling to 0. But B, you get 0 and 1. Now we can't have that. Since B changes, we remove it from the equation entirely. We don't need to worry about it. So in this case, we only need to look at A. So we have A equaling 0. To actually make this useful to us, we do A naught. So A naught, which you can represent with a line on top or a dash on the side, gets you 1. So your sum of products here would be F equals A naught. This is your most simplified equation. Now we can double check this by just looking back over here. So our F is represented by A naught. So let's go through this line by line. At A0, if we take the naught of 0, we get 1. So A0, 1, check. A0, 1, check. 1, 0, 0, that holds true. 1 becomes 0 yet again. That holds true. So that would be our sum of product. Now, if we were to go ahead and instead of doing sum of product, do product of sum, let me undo all of this work over here. And do product of sum instead, we would circle zeros. So here, we'd circle this. Now, again, this is very similar. We just have F is equal to A. F naught is equal to A. We say F naught because we're circling our zeros. We can check this again, or if you really wanted to, you can switch it and say F is equal to A naught, but that would be improper. That puts us back in sum of product form in this case. So we'll erase that and we'll look at F naught is equal to A for our product of sum form. So whenever A is 1, we should have 0. Or we can look at this in reverse. Whatever F is, A should be the opposite. So we can check up here yet again. F equals 1, A equals 0. That's true. F equals 1, A equals 0. That's true. F equals 0, A is 1. Correct. F equals 0, A equals 1. That holds true. So remember, product of sum, we circle zeros. Sum of product, we circle ones. Now, you may get some things like this. It won't be a direct truth table, but rather you are provided a summation. With the provided summation, we can create our list. Now, seeing how this only goes to 6 total numbers, we will assume that we only have 3 variables. How do I know we have 3 variables? Because since this is all in base 2, 2 cubed gets you 8. So we have 8 possibilities if we have 3 variables. And since we are given 1, 2, 3, 4, 5, 6 total numbers, we can go ahead and just assume that we have 3 variables unless otherwise stated that we have 4. So let's go ahead and choose our 3 variables. In this case, I will just choose A, B, C. So A can either be 0 or 1, nothing else. Let's look at BC. 0, 0, 0, 1, and remember, a difference of 1 bit. So 0, 1 becomes 1, 1. And then we have 1, 0. So let's go ahead and construct our K-map. Remember that the numbered value on the interior can be given by our bits. So A, B, C, with A being our most significant bit, our MSB, with C being our LSB, least significant bit. So let's go ahead and go through this. So at 0, we have a 1. At 1, we have a 1. I'm going to skip over 4 or 3 and go to 2. At 2, we have a 1. At 4, we have a 1. At 5, we have a 1. And at a 6, we have 1. The remaining portions will be 0. That is 4, 0, 1, 2, 3, 4, 5. This right here will be 6. 0, 1, 2. Oh, I see. This right here should be 0. That should be 0. 0, 1, 2, 3 is skipped. Then we go to 4, 5, 6. Skip 7. That's my fault. See, it can be a bit confusing. Now, we have 2 choices from here. We can go sum of products, or we can do product of sum. Now here, we're going to go both, but I just want to point out we only have 2 zeros here. And this would be a much easier equation if we just do product of sum. So let's go ahead and find product of sum very quick. So we go ahead and we'll circle this. Now, remember, when you're doing this, since you're circling the zeros, you're doing F naught. Is going to equal, we have B or C, and then remember, we have A. So our B is always 1, our C is always 1, our A is 0 and 1. I'm getting these values from this over here. Since we're circling down this line, you can just compare it with the values of A, which just gives us 0, 1. Since A changes value, we can disregard A. With that being said, we have F naught is equal to B or C. And that is our statement here. This would be our product of sum form for this. So I'm going to go ahead and write that up here. F naught is equal to B or C. Go ahead and erase that. And I'm going to go ahead and rewrite this right over here. 0 and 0. Now, for sum of products, we circle the ones. Now, you want to circle as much as you possibly can in order to disregard as many values. And so here we have a choice of 4. I'll go ahead and circle that. I'm going to label that C1, circle 1. Now, watch out for this. This right here is 2, right? However, you can actually circle more than that because 1, 0 and 0, 0 differ by 1 bit. You can go from the side over here to this side over here, and that gets you C2. and that will actually cancel more terms than if you were to just do the top and if you just circle the two variables themselves. By circling 4, you'll actually be able to cancel out more. So let's go ahead and look at our C1. So our C1, B is equal to 0, C 0, 1, A 0, 1. A changes, C changes, our only value is B. B equals 0. Since we're doing sum of products, we need to make sure that this equals 1. So we need to do B naught equals 1. So C1 equals B naught. Let's look at C2. For C2, we have B is equal to 1 and 0. Then we have our C, which is equal to just 0. It never changes. And you have our A, which goes from 0 and 1. B changes, A changes, C is equal to 0. This needs to be sum of product. So C naught equals 1. So our C2 is just C naught. Our F will be described as C1 or C2. Because of this, we'll say F is equal to B naught or C naught. So top is our product of sum, bottom is our sum of product. Now, notice how much faster we were able to get our product of sum. We had to do far less work because we only had to circle 2 variables, or 2 bits. Meanwhile, our sum of product, we had to circle 2 groups of 4 and do some cancellations. So unless it's stated otherwise on your exam or your homework or whenever you're doing these K-maps, choose for the smaller amount. You don't want to do more work than you have to. It's easier this way, it's faster, it's smarter. Alright, we are going to look at don't cares. What are don't cares? This is a don't care. Now what is don't care, you might ask? It is in the name. You simply do not care what it is. It can either help you or it can hold you back. So we have our truth table here. Let's draw it out. A, B, 0, 1, 0, 1. Draw this bad boy out. Bam, bam. So 0, 0, we have 0. At 0, 0, 1, we have 0. At 1, 0, we have 1. And then at 1, 1, we have a don't care. Now, don't care, you can treat it as either a 1 or a 0. It can be whatever you want. It can help you here. So remember, you want to circle as much as possible in order to cancel out more of the variables. It makes your overall equation easier. And so, as always, we're going to do this in both forms, sum of product and product of sum. Let's do sum of product first. So to do sum of product, we want to circle as much as we can. Here we go. Because we can treat this don't care as a 1, it will actually help us out here. So let's find out what happens on this circle. So with what we circled right here, let me write this a bit bigger. A is going to equal to just 1. It never changes. B will go 0 and 1. B dies. All we have is A. And since A is already positive, we don't have to worry about it. F is just equal to A. Remember, you can always check this by looking back at your original truth table. So when A is 1, F is 1. Now, what if we didn't circle this don't care? Let's go ahead and undo this. Here we go. What if we didn't circle this don't care? What if we just went for the 1? Well, you have A equals 1 and B equals 0. So A stays as A, B becomes B naught. Our new equation is F equals A or B naught. This is more convoluted than our first equation that we found, F is equal to A. So by incorporating our don't care, we actually get a better answer. Now, you're going to see now in just a second, when we do product of sum, it's going to be the opposite. So let's go ahead and erase this. This is a 1. Let's go ahead and do our product of sum. Product of sum, we circle our zeros. So we can go ahead and circle that. And we have circled all of our zeros. We could keep going, and we could go ahead and circle this, but that will just add another term. But let's just go ahead and do it anyways. So product of sum. Remember, our initial was just A for our sum of product, SOP. For product of sum, we have A is equal, C1, C2. C1, you have A is equal to 0. You have B is equal to 0, 1. B changes, A stays. A can actually just stay because we're doing product of sum. So A just stays at 0. So for C1, we have A equals 0. Now let's look at C2. C2, we have A equals 0, 1. We have B is just equal to 1. A dies, B becomes B naught is equal to 0 because we're doing product of sum. So C2, B naught is equal to 0. So our final thing, F naught is equal to A like that. It's going to be equal to our C1 and our C2. So our F naught is going to equal to our A and our B naught. Now, this is if we incorporate both C2 and C1. This is if we include the don't care. Now, we could just completely remove the don't care because we had circled all of our zeros already. You don't need to worry about the don't care unless it helps you out in creating a bigger structure when you're circling. So rather than including C2, which has our don't care, we can just have C1. And our C1 just gets us A. So F naught equals A, or F naught equals AB. F naught equals A is our simpler answer. All right. Now, if you haven't seen this symbol right here before, this is a capital pi. This is how you indicate product of sum. Now, over here, we have 1, 2, 3, 4. We have 4 values here. Now, this indicates, unless otherwise specified, that this is a 2-variable system. How do I know it's 2? That's because 2 squared equals 4. If this was 1 variable, we could have up to 2 possibilities. 2 squared, 4, 2 cubed, 8, 2 to the 4th, 16. So since there's nothing else here, we can go ahead and assume that this is just going to be 2 variables. A, B, draw this out. Zero, 1, 0, 1. At 0, we have a 0, because remember, this symbol means product. We're doing product of sum here, or we're running out product of sum. At 1 we have 0. At 2 we have 0. At 3 we have 0. Alright, so what do we have here? We have a full K-map with just one form of value. Now, this poses a problem because if we're going to do product of sum, we'll go ahead and circle all of this. But what happens here? We have A equals 0, 1, B is equal to 0, 1. So A changes, but so does B. Now, what does this mean? Well, this is actually very simple. We have F is equal to 0. That's it. If this is product of sum, F naught. So just remember this. If it is one single value, the F will always carry that value. Now, let's say we have a K-map that is actually a 4-variable K-map. We haven't done one of those yet. So we have A, B, cross, C, D. Recall, A is your most significant bit, D is your least significant bit. So let's go ahead and write this out. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Draw this out, close it off there, close it off there, close it off there. And remember, 0, 1, 2, 3, 4, 5, 6, 7. And then we jump to the bottom left corner. 8, 9, 10, 11, 12, 13, 14, and finally 15. So this, we're just make something up on the fly. Let's do 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1. Why did I pick this? Because I want to show you a trick. Let's do sum of product for this. So we circle the ones. Let's go for the obvious. This center one right over here. So for our circle 1, we'll go ahead and label this C1. Now we're working with 4 variables. Let's start with A. So with A, we go from 0 and 1. With B, we have 1. For C, we look at the top over here. Look at this value. Those two values right there. So C is 0 and 1. D is just 1. So remember, if it changes, it dies. A is dead. C is dead. All that's left is B and D. So for C1, we have B, D. Now, what about these individual ones? What do we do about them? Do we go about and circle each one individually? Well, let's look at the bits real quick. So similar to when we have 3 variables, with 4 variables, it's a bit of a trick. So frankly, you can consider a 3-variable K-map a bit like a cylinder, where things touch each other on either side. So at this point over here, here's the same point over here. You can consider a 4-variable K-map a bit like a sphere, where all the sides are shared. That's a bit confusing, but that's how it's often described. So we have this piece right here connects to this piece right here. How do I know this? The top left bit it is represented by 0, 0, 0, 0. The top right bit is represented by 0, 0, 1, 0. Difference of 1. Great, so we have one circle there. But we're not going to stop there. We can actually circle 2 more with this. Let's compare the top left and the bottom left. 0, 0, 0, 0 versus 1, 0, 0, 0. That's a difference of 1 bit. We circle that one too. Let's compare the top right and the bottom right. So for our top right, we have 0, 0, 1, 0. For our bottom right, we have 1, 0, 1, 0. Yet again, a difference of 1 bit. So we can circle this one too. Now, what does this all look like? We have C2 for that. C2. So let's look at these real quick. So for C2, let's go ahead and get started with A. So our A is 0 and 1. 0, 1. Our B is 0 and 0. So it's just going to be 0. And our C, we're looking now at the top. We have 0 to 1, 0, 1. Then we have our D from 0 to 0. We say 0. A changes so it dies. C changes so it dies. All we have left is B equals 0, D equals 0. We're doing sum of products, so these needs to be knotted. B naught equals 1. D naught equals 1. Therefore, C2 is going to be B naught and D naught. So our sum of products is going to be F is equal to B D or B naught D naught. Now, if you know your gates, you will recognize this structure as a XNOR. So this could be simplified a bit more because K-map only works off of the basics of product of sum and sum of product. So this can actually be written as B XOR D, all of which is knotted. But that's a bit more complex. If you recognize that structure, you'll be all good. But this right here is good enough for our sum of product. Now, product of sum over here would be quite similar, except in this case, we just circle the top 2 and bottom 2 as 1, the 2 on the left and 2 on the right as 1, and that would be your 2 circles, and you'd go off of that. And we'll leave that as an exercise for you guys, because I believe in you, and I think you guys can handle it. I'm going to start that question in just 1 second. So we're going to go ahead and do that. Circle the top, circle the bottom. We're going to ignore these. Ignore this one, ignore this one, ignore this one, ignore this one. We're going to circle the far right 2, the left 2. So for the top, we're going to call this one C1. For the right, we're going to call that one C2. So product of sum, POS, C1. How does A change? A goes from 0 to 1. B goes from 0 to 0. C goes from 0 to 1. D goes from 1 to 1. C2 goes from A goes from 0 to 1. B goes from 1 to 1. C goes from 0 to 1. And D is 0 to 0. So just 0. Let me double check my C1. D is also just 1 here. So our C dies, or A dies for both of these. B for our C1 stays as B. D becomes D naught. For our C2, B becomes B naught. D stays as D. So our F naught for a product of sum for is going to be B or D naught ANDed with our B naught or D, which is the exact thing that we have over here. Yet again, if you recognize the XNOR, this is XNOR in its product of sum form. So it is important to recognize these things out in the wild when you're working with Boolean algebra, because they can help you simplify things even more beyond just the Carnegie map. Because remember, the K-map only simplifies things with sum of product and product of sum. But that is all that I have for you guys. So just a quick highlight. Remember, two forms, sum of product, product of sum. We circle as many elements that we can as long as it follows the form of 2 to the n, with n being our variables. There are, or at least for our concerns, 3 forms of the K-map, 2 variable, 3 variable, and 4 variable. Remember that you can only circle ones and zeros that are exactly 1 bit different. And that can make you do some very interesting things, going from corner to corner, going from edge to edge. Just remember to practice. Go ahead, Google some more exercises. I hope this video was at least helpful in some way and able to clear up and show you some tricks. Beyond that, you can always visit us at How Beta Pi. Thank you very much. Good luck with your studies.